All right, so what we're going to learn today is how to find the rate of change of the surface in any direction desired. So I want to take a brief moment to recall what we did in a previous section. So we had a surface in space, z equals f of xy, and we had a point in the xy plane. So let's suppose that point has coordinates a, b, 0. So it's in the plane. And if you take that point and project it up so that you're on the surface, okay, so that point would be AB, f of AB. And we learned how to find the rate of change of the surface if you're only considering the direction of x. That was called a partial derivative with respect to x. And likewise, we learned the rate of the change of the surface with respect to y. So let's do just a brief demonstration, draw one picture, and then we'll move on to the directional derivatives. If I were tasked with finding the partial derivative of f with respect to x at the point AB, then what I would do is cut the surface with the plane y equal b. So imagine taking a plane that's parallel to the zx plane and cutting through that surface. That's going to create a curve. Okay, so let's say that curve right there is C1, right? So what's true about every single point on that curve is that its y coordinate is b. So the only thing that's changing is x and z. If I considered the tangent line to the curve, that geometric interpretation was the rate of change of the surface in the direction of x. So what we would have to do here is take the derivative essentially. I'm not going to go through an example because we did a lot of these. But the geometry behind it is the rate of change of z equals f of xy in the direction of x. Okay. And again, it's the slope of that tangent line. So what that gives you is the steepness of the surface if you're only considering moving or pointing your feet in the direction of x. Okay? The direction of x can be represented by the unit vector I. If you recall what the unit vector I is, that vector is 1, 0. So we're going to learn in a minute that I can actually move not only in the direction of x and the direction of y, I can move in any direction I want to move in the xy plane. So if you're sitting at this point and you'd rather know what's the rate of change of the surface if I move in that direction, that's called the directional derivative, and that's what we're going to discuss now. So if you consider the graph that you see here on the right, your surface is obviously the big blue bowl-looking thing, and you've got a point here. This is what my AB0 was, so that point's in the xy plane. You take that point, project it to the surface. So you're standing on this surface, okay? And you want to know, how steep is the surface? If I move in the direction of this unit vector, and that looks to be maybe right about a 45-degree angle. Okay, so we call that vector, so that red vector there is u. Let's see where I can write this. So u, let's put it up here. U is this red vector in the plane. Okay, if you cut the surface with a plane determined by that direction, okay, so this green plane that you see here is the plane that you're cutting through the surface with. That creates a curve, okay? So now you've got a curve. If you've got a curve, you can find the slope of the curve, Okay, and that's what this black tangent line right here represents. So we call this a directional derivative. So what I want to do is write down the general definition first, and then we will move to some examples. There are two things you need. Actually, let me start down here. The directional derivative of fz equals f of xy at the point P whose coordinates are x naught, y naught. So that's the point in the plane that in the xy plane that you're sitting at. So in this illustration, your point would be AB0 in the direction of the units vector. So it's got to be unit. U equals, I don't want to use AB because I've already used those letters, so I'm just going to call it U1, U2. Probably in future problems I'll probably default to AB is. Okay, the notation is a bit awkward, but the computation is not that bad. So here's the notation we have. D sub u, that means directional derivative in the direction of u at the point x naught, y naught. Okay, I know that the output is going to be a number because we're talking about the slope of the surface at that point. So the way we calculate it is we take the partial derivative of f with respect to x, plug in the point p, which in this case is x naught, y naught, multiply by the, I meant to call, oh no, here we go. So multiply that by the x coordinate of the unit vector, which is u1, plus partial derivative of f with respect to y at the point x naught, y naught, times the y coordinate of the unit vector. Okay, so these are the components of the vector. These are not vectors, these are just the components. And that output is going to give you the slope of the surface at any old point in any old direction that you want. So we will follow with lots of examples of how to compute it.